Hello, everyone. Um, Today we are going to talk about the junction capacity. And previously, we have already derived a formula for the division width. The formula is like that. Uh, Let's see, division width. If your memory serves you well, it is like this. So Q, and then the junction voltage. The building junction voltage, and then divided by the epsilon. The epsilon is the permittivity of the medium, ivory silicon. The epsilon is 11.8, and then the doping concentration, 1 over Na and 1 over Nd. So this is the division rate. And what you need to know about this division rate is literally it is a capacitor. Why? If you have a semiconductor, this division region is the only region with the electric field. And the P type and N type. So cos, and the electric field is pointing backward, pointing to the left side, from positive to negative. And your the division rate is here. So what happens if you apply the bias? Now it is an unbiased condition. And if you bias it, yeah, under a reverse bias, and what is going to happen? Under a reverse bias, oh, yeah, let me use WD, yeah, WD, yes, then you will mix up. Under a reverse bias, then what happened, right? The the junction voltage is going to be uh, Vj minus Va, where Va is the high voltage and is a negative value. So in action, uh, you can say that right, is equal to Va. Uh, you can say this, right? Uh, the junction voltage. Uh, Now, what I'm going to do is examine what is going to happen when the voltage here become this value. So obviously, this value is bigger than is bigger than Vj. So in other words, right, the voltage is changed. Apart from that, the concentration remain constant, and the electron charge is the same, a constant, and the permittivity is the change. The only thing that is changing is the voltage. If the voltage here is increased to this extent, then the division width will be widened. So now I need to write down the, yeah, let's write down the important information here. The under a reverse bias, yeah, the new diffusion width is going to be like this. VA, the high voltage, and then so the new diffusion width, right, is going to be wider. So this is something that I want you to know uh, in these lectures. And now the diffusion width, well, you have already got the information for the diffusion width. Not very good, man. I need to change the formula. Sorry. Um, the new diffusion width is going to be greater. This is one thing I want you to know. Uh, so WD dash to Q VJ plus VA. And then 1 over NA plus 1 over ND. Now, how about the capacitance? Originally, the capacitor, nothing about this region. It is literally a capacitor because this division region is equivalent to a parallel phase capacitor. And the separation here is WD, which stands for the division width. And the area here, right, we don't know. And we know that there is an electric field. And we also know that there is a charge, right? The charge, you have to make sure the positive and negative, right? We need to know that the charge, right? The charge is different. So literally, it is a capacitor. And a parallel phase capacitor. You know the parallel phase capacitor, right? If you have done high school, everyone should know that. The parallel phase capacitor is epsilon A divided by D. Yeah? Uh, if you want to know the capacitance per unit area, uh, the capacitance per unit area, then maybe you have a little c here, yeah? E, it is equal to, uh, C will be equal to big C divided by A. So in other words, right, it's like this, and the D, yeah? From now on, we are not going to use this D because the separation here is already uh, dictated by this variable, which is WD. So let's use this one. Now WD, yeah, we haven't finished the story yet, right? We have an epsilon, the permittivity here. But then we have already learned the division width, right? We better do it. And now we will better label this variable, right? C naught is equal to, in an bias condition, then you got Q, V, J, and then epsilon and A plus and D. So this is easy. Now, what happens if it is biased? So let me write down, right? Uh, for unbiased condition, right? For unbiased PN junction. The question is, if it is biased, what we are going to do? So now I'm going to switch to the other side of the block. We don't have enough space. If it is biased, then you have to replace this division with the new one. Now I'm going to do it for you. Uh, the new division wave, right? We have this formula, and now we are going to erase this space. Otherwise, we cannot survive. So under a bias, under a reverse bias, yeah? Remember, right? Reverse bias. If you use forward bias, then the division wave will be narrower. VJ, the junction voltage, right? Junction voltage is the junction potential is equal to VJ plus VA. Yeah, the absolute value. I'm going to use the absolute value to make sure we don't have any confusion. It's plus, right? And the capacitance per unit area. The capacitance per unit area is going to be, yeah, for example, this is C, yeah? This is a CX, right? Let's say a CX. CX. Maybe CR is better. CR means the reverse bias. Uh, Under a reverse bias. And let's see what happens. CR, yeah. Again, it is epsilon divided by the division width, like what I did before. This formula, yeah. But the only thing different is that the VJ. Now we are going to do it carefully. Two, and then Q, and then this bigger voltage, right? VJ plus VA. And then 2. And then 1 over NA plus 1 over ND. Now, before further manipulating the formula, right, I'm going to work out, I'm going to just uh, tie up this equation because this equation is too often now. What we can do is we extract VJ, the junction voltage here, to here. So T not VJ, yeah. Yeah, we move this to up here. Then we got a new equation. Yeah, it's not really new. And then 2Q epsilon 1 over NA plus 1 over ND. Yeah. So I just need to use this expression because this one is too difficult to handle. So according to equation 2, now I'm going to further manipulate this expression. Right? Again, I will take off the formula here. Okay. Now you have this bit here, 2Q over 2, 1 over NA, 1 over ND. Yeah, look, according to what you have got here, uh, this expression is equal to 0, uh, and this C naught times the square root of VJ. So it's easy, right? We can just do it here. Yeah, we just replace it, right? Because we have the expression here. So it's easy for us to handle. And let's see if we have enough space here. Not much, right? So we just do the simplification on the fly. Okay? Now we have the expression here, then this one is going to be E dot Vj. Yeah? And now you can move this expression to the bottom. Yeah, that's easy. That's easy, right? Then one, and then uh, here is Vj. Yeah. So that's very easy. So this is the new formula. Uh, the C naught here is the unbiased junction capacitance. Uh, C naught is the unbiased junction capacitance. Capacitance density, right? Precisely. So unit area, right? Perhaps. Yeah, we don't have enough space. Yes, just enough. So now we have already derived another formula, right, for this lecture. I think the information is just good enough. Uh, and thank you very much for your attending the class. If you have any question, please do not try. Don't be shy. Just leave your question in the comments box, and we will answer your questions if we have time. Thank you very much.